So I'll let you read all of this, so feel free to pause it and have a read of this now. But basically, the gentleman's looking at an average rate of 150 orders per hour. Now, what we're looking at in today's video is the Poisson distribution. Now, we've already looked at the binomial distribution, which would say, for example, if I was to shoot at a target and the chance of hitting the target is 0.9, what's the probability I hit the target exactly 7 out of 10 times, exactly 4 out of 10 times, or less than 4, greater than 6, so on and so forth. Now, what we're looking at here for the Poisson is we're looking at stuff happening over time. Now, they say that they've got an average of 150 orders per hour, and basically you're asking, how can they predict how many orders per hour they'll have, or how many orders they'll have over the next time aspect? Now, what they then did was take a record of the number of orders every minute. Oop, wrong table. There we go, just erase it. Now, they then said how many orders they have per minute. And so they observed 70 minutes where there were no orders, 215 minutes where there was 1 order, 265 where there were 2, 205 where there were 3, so on and so forth. And having got all of this, what they then did was they then had a look at the stats behind it. Now, the stats behind it came out as n being 1000, sigma fx being, now notice I've just got greater than 7 here, and that's quite an important point to make, because actually I need a value, and the value that I'm using is 8, because what's going to happen is, as you think, how many orders will I get per minute? I could get 7, 8, 9, 10, I could even get 1,000,000. The chances of it, 1,000,000 happening, shrink quite a lot. I could win the lottery, chances of not. Lottery isn't a time aspect, there's more of a binomial aspect, but hey. No, in fact that's combination permutations, S1. So I'm going to put down an 8, and I'll fix it an 8 because 9 is less, 10 is less, so on and so forth. So that gives me sigma fx as 2525, and then sigma fx squared as 8885, which totals me up as x bar being 2.525, and their mean as well coming out to be, not their mean rather, their standard deviation coming out to be about 1.58. Now I'm also going to put in s squared because that's quite important. Now that was to 2 decimal places, 3 significant figures, and the previous number squared is 2.51 to 3 significant figures. So this information is quite important. Now when we're dealing with orders over time, what we're going to model as, rather than a fixed number of trials, we're going to model x as Poissonally distributed and having a mean of lambda. That's lambda, I say no for some reason. So Poissonally distributed with a mean of lambda, which means that x in this case is going to be Poissonally distributed with, now remember these are our observed frequencies, and so I just need to check up 150 orders per hour, so 150 orders in 60 minutes. 150 divided by 60, that is 2.5. So x is Poissonally distributed, and they say with a mean of 2.5 orders per minute. Now notice, actually when we observed it, way, look at that, our mean is pretty much the same thing. And this is one of the properties of the Poisson distribution. For it to be modelled as a Poisson distribution, your means have to be the same. But as well as that, notice our variance, 2.51. Our variance is actually pretty similar as well. And that is important. The mean and the variance both have to be about the same value as lambda, for a Poisson distribution to be able to work. So what we're going to do is test to see what we expect to get if this was a Poisson distribution, and then see whether or not a Poisson would then be appropriate to use. We're not actually going to use it to model it, we've got the numbers, but you'll get the idea. So if we are going to use a Poisson distribution, then I'm going to need to know how to work out the probabilities on the Poisson distribution. And for the Poisson distribution, the probability that x is equal to r is going to be e to the minus lambda times lambda to the value of r over r factorial. So if I want to say, for example, what is the probability that x is equal to 4? Well, I observed in this month gone by that there were 125 out of 1,000, so the probability is 0.125. And if I work out theoretically what the probability would be if I modelled it as a Poisson, then that will be e to the minus lambda, so minus 2.5, times lambda to the 4 over 4 factorial, which comes out to be 0.1336, and that, although not the same, is actually pretty similar. Now if I was to do that with all of them, so probably the x is 3, x is 2, x is 1, and see how they compare in probabilities, or in this case I'll do it in frequencies because I know they did 1,000, so I'll times all my probabilities by 1,000, so 134 orders compared with 125, I should get a table. So hang on, and this is the table I get: 70, 82, 215, 205. So the numbers are actually pretty similar, and that's what you want. If I was to do a graph of these, you'd see that actually it's not perfect. It probably won't be perfect, but it is pretty similar for what we're looking at. Now, this helps us immensely, because then I could say, well, in theory, if I wanted to work out not in the month we've just observed, but in the next month, the month after, what's the probability of getting 4 or less orders a minute? So that's 4 down to 0. What's the probability of getting 2 or less, much like we did in the binomial? And to do that, what I'm going to need to use is my formula book. Ta-da! Now, my formula book's already up here because I've recorded this video once before, but with no sound. So, I'm on page 20 of it, 18 rather. Here are the Poisson distribution probabilities. You've already seen these ones, which are the binomial, and so after the binomial section comes the Poisson. Now, each of the tables has a little bit of information next to it. So we've got lambda, which is our mean, and then the probabilities accordingly. Notice they don't go all the way down to 1,000 if they don't need to. What it's saying is if I have a mean of 0.07 calls per minute or whatever it is, then actually after 3 the chance of it having 4 is pretty much guaranteed. You're going to have 4 or less. Now these are cumulative probabilities, so it's the running total. So this would be 3 or less is 1, so 4 or less, well, it's just going to be 1. 5 or less, it's just going to be 1. I don't need them all. Now we're looking for a mean of 2.5, so I'm in this table here, and so if I just get this table to write on, hang on, et voila, what we're looking at is we're looking specifically at the following. So we have lambda is 2.5, and actually I want to see what 4 or less is, and 4 or less is going to be that value. That specifically gives me, just like in the binomial, the value of 4 or less. Should I want to work out, for example, the probability that x is equal to 4, which I already have, I know is 0.1336, then what I can do is say that is equal to the probability that x is less than or equal to 4, which is 0.8912, minus the probability that x is less than or equal to 3, which is 0.7576, this number up here. And then if I do that, actually I do get that answer. So rather than have to use my formula, this bit here, what I can do is I can just use the tables to help me. And in the majority of questions that we do, or that you'll see in the examples, and you'll probably end up using the tables quite a lot. If you need to find a specific value, x is 4, x is 6, x is 9, then you use a formula. If you need to find a range of values, then you start looking at the tables. Now obviously when we're doing a Poisson distribution, we need some idea of when we're going to model Poisson distribution. And generally speaking, here it is. A discrete random variable may be modeled by a Poisson distribution provided events occur at random and independently of each other in a given interval of time or space. The average number of events in the given interval, lambda, is going to be uniform and finite as well. So you can't have like an infinite average. But it's going to be the same consistently all the way through your intervals. So if you have an interval which is, say, as we have, a minute long with 2.5 phone calls per minute, then for the next 1,000 minutes, it will always be an average of 2.5. That's what that's looking for. Now, you already have your little formula. What I want to do is I just want to go through how this little formula is actually made. So I'm going to do a little side shoot off here. I need a pen. And show you how this bit comes about. Now, one of the beauties of probability distributions is you know that the sum of all the probabilities from your binomial should equal 1. It's a criteria. I roll a dice, the probability of getting a 1, 2, 3, 4, 5 or 6, well, they're all going to add to 1 because I will get one of those numbers. And the same applies here. Now we're actually using a value of e in there, which we've seen in core 3 and core 4, but when you reach your sequence and series in the further maths, you'll come to find that e to the x is actually 1 plus x to the 1 over 1 factorial plus x to the 2 over 2 factorial, so on and so forth, up to x to the r over r factorial, and then it'll carry on as well, because it's an infinite series. Now, what I'm going to do is try and fudge this so that all these numbers on this side add to 1. Now, they don't add to 1. So to do that, what I need to do is divide by e to the x for everything. Now remember, dividing by e to the x is exactly the same as timesing by e to the minus x. So that will give me e to the x over e to the x. I'll divide it on this side to make it easier to see. Then I'll start timesing. So this will be e to the minus x times 1 plus e to the minus x times x to the 1 over 1 factorial plus e to the minus x, and you get the idea, x squared over 2 factorial, and it'll carry on. Now if I just swap over the x's for lambdas, then obviously I'll have the 1 on one side, e to the minus lambda times 1. Now I'm going to hide 1 a little bit, because actually what it's going to be is lambda to the 0, anything to the 0 is 1, over 0 factorial, and 0 factorial is 1, plus e to the minus lambda, lambda to the 1 over 1 factorial, plus e to the minus lambda, lambda to the 2 over 2 factorial. You get the idea. And so in essence, that's where it actually comes from. So when you start doing the further pure maths, you'll see that the sequence and series that you use actually have an application in the statistics side of things. Now, you don't need to know all of that. Like I said, it's a bit of a side, but that's where this particular formula comes from. Now, having seen this little video, one thing you might want to look at is the recurrence relations, and not to use it, use the tables. But if you're interested, to get, for example, from x is 0, then to get to x is 1, you multiply the previous term by lambda. To get from x to 1 to x is 2, you multiply the previous term, so we'll do it here. So this one here, that's 1. So if I multiply this number by lambda, well, I'll get there. If I multiply this number by lambda over 2, then actually I'll get to that one. If I multiply this one by lambda over 3, I'll get to the next one, and so on and so forth. It's not something I use, but feel free to look it up in the book, because it is actually quite interesting. So have a look at example 1.1 and example 1.2, and then have a go at exercise 1a, and then there'll be another video after this.